Hello and welcome to the Terran Space Academy, where we help prepare you for a bright future in the space industry. Please don't forget to like and subscribe, and help support us on Patreon if you can. We also have Academy-themed gear in the Academy store. We did a full video on thrust vector control mechanisms for rocket engines, and we'll play parts of that in this video. But today we're going to focus on recent advancements SpaceX just made. SpaceX uses Raptor engines, which have a mass of around 1,500 kilograms each. It is important to remember that thrust vectoring occurs under thrust. The rocket engines will be pre-positioned before ignition. Under thrust, G-forces are created, so engines have weight, both on a planet or moon and in flight. Moving that much weight around takes a lot of force. SpaceX has been using hydraulic actuators, and we'll review those first. This is the 3D printed Rutherford engine by Rocket Lab. The Rutherford is a beautiful 3D printed engine. I often get pushback on the importance of 3D printing for space industry. I'll save that argument for another lesson. But you can see the beauty this technology can create. Now I want you to look at these actuators. These are here in blue. These are the vector control actuators. These can be electric motors with a worm drive for very small engines, like Vernier engines. These are precise and don't move if not activated. Or hydraulic actuators for larger engines. If we freeze here, we see the input and output lines for hydraulics. The Astra Delphin engine will be very similar, as both these engines use electric propellant pumps. We will also look at the Firefly Alpha rocket. The Alpha rocket uses the Reaver 1 engine. The Reaver engine is much bigger than the Delphin engine used by Astra, or the Rutherford engine used by Rocket Lab. The Reaver 1 engine also uses a tap-off cycle to power its turbopump, instead of electric motors like Astra and Rocket Lab. We'll look at that later. Let's freeze the video and identify some parts. Here is one electropump in red. That's my new word for an electric, not a turbopump, and I'm sticking to it. Here are the propellant lines. MOV stands for main oxygen valve, and MFV stands for main fuel valve. Here we can see a full view of this. The oxygen is pumped into the combustion chamber, while the fuel is pumped through cooling channels in the engine before going in to be burned. So the red pump here is moving the liquid oxygen, and here is another electropump in green. This one is for the RP-1 rocket fuel. Here we see the two actuators. Looking at the actuator, you can see that this is a smaller cylinder telescoping into a larger one. If you are unfamiliar with hydraulics, please review this lesson. Here we see the swivel at the thrust plate, and one down here on the engine. In this neutral position, all the force is projected straight up through the rocket. If this cylinder is extended, it would swing the engine this way, to our left. That would put an asymmetrical force on the bottom of the rocket, causing the base to pivot in this direction, as you can see here, which causes the nose of the rocket to pivot in the opposite direction. So if you want your rocket to go left, point your rocket engine to the left. To go right, point it right. This is how a single rocket engine works. Rocket engines rarely swivel more than about 5 or 6 degrees. Otherwise, the shear force generated could tear the rocket apart. You can also see that these two actuators are set about 90 degrees apart. This setup can actually let an engine move in any direction. To see how this works, we will look at a video by Stanley Creative. Artists like this, through their hard work and beautiful art, can make concepts much more understandable. Here we see 3 Raptor engines. Let's watch how 2 actuators can move a rocket engine in any direction. We see the actuators on each engine. The engines are attached, and the actuators are adjusted to swing them side to side, or front to back. Now understand that a Raptor engine has a mass of about 1,500 kilograms. That is the same as a small car. These are incredibly powerful hydraulic actuators. Quite a bit of the plumbing you see on a Raptor is for the hydraulic control of valves and engine positioning. Now let's watch a single engine do something amazing. This is a video of Starship test number 5. This has one Raptor engine that is offset, meaning it is not attached to the exact middle, but is off to one side a little. They had to do this because they will put 3 engines in the middle, like our previous video showed. Here we see the one rocket engine lift the structure into the air. Let's pause here for a moment. The rocket is firing almost vertically, but the tank is leaning to our right. We'll fly a little more and pause again. Now we see the tank is almost straight up and down, but the engine is firing a little toward our right. This is to move the rocket to the left side of our screen. Just like you would balance a broom on the palm of your hand, this engine, controlled by a fast computer and some smart programming, is balancing this rocket, moving it over from the launch pad to the landing pad. We can see the engine making final adjustments. These delicate adjustments are amazing, because again, this is a massive engine. It is vital that there be very little lag time between command and response, and feedback detection must be just as fast and accurate. If we run out of hydraulic fluid, things don't go well. But what if you have more than one engine? Then things change. Let's look at 4 different systems. Here is the Firefly Alpha with 4 engines. Here is the Astra Rocket 3.3 with 5 engines. And here is the Rocket Lab Electron rocket with 9 engines. This is the same configuration as the SpaceX Falcon 9. Rocket engines are fairly simple in some ways. Pump in fuel and oxidizer and ignite them. Keep pumping in propellant and your rocket engine keeps working. Stop the propellant and it goes out. The only major moving parts on a rocket engine are the actuators, the valves, and the turbopumps. Very small rocket engines can be pressure fed, but as tanks get larger, this becomes impractical. This Lynx spaceplane used a unique piston type of propellant pump, but most rockets use a centrifugal pump, which spins an impeller to move fluids. On the Electron and Astra rockets, these are spun by an electric motor. On the Firefly Alpha, the Reaver 1 turbopumps are spun by running an exhaust pipe from the combustion chamber. This is called a tap-off rocket engine. And the Blue Origin BE-3 is also a tap-off rocket engine, by the way. After powering the turbopump, the exhaust is dumped overboard. You can see the 4 exhausts here. The Merlin engine has a preburner to supply power to the turbopump. This is also dumped overboard, but can be put down the inside of the nozzle for cooling it. The Raptor is, of course, full-flow staged combustion. It has a preburner for the oxygen side and one for the fuel side. In a Raptor, no propellant is wasted. But all of these systems do the same thing. They spin an impeller blade at tens of thousands of revolutions per minute to pump huge amounts of fuel and oxidizer into the combustion chamber. These spinning blades can fracture, sending shards of metal out at high speed to tear up your engine. You usually know when this happens, as your rocket engine blows up, and usually so does the rocket. Here again, we see an Antares rocket doing just that. This has been a major cause of rocket engine failure. But other things can go wrong too. Here we see the recent Astra Rocket 3.3 launch. Immediately after launch, one engine fails. We don't see anything explode, and since this is an electropump rocket, one of the pumps could have lost power from a failed electrical connection, or a hydraulic leak could have caused a valve to close prematurely, shutting off propellant flow. Let's watch one more. Here we see the Firefly Alpha launching. Everything looks great, and we watch again from different angles, even inside the engine bay. As the rocket climbs, all engines are running. The rocket would have aborted the launch if all engines had not fired on startup. Now watch closely. We see one engine here sputtering and going out. The rocket adjusts for this loss and continues. The control software, by vectoring the thrust of the other engines, is able to stay on course. It does this by gimbaling the other engines. Here is what the base of the Firefly Alpha looks like. As you can tell by these open areas, these engines can gimbal. One engine has failed, and as the rocket starts to fall in that direction, the others gimbal to push it back on course. The rocket continues to climb. Losing an engine has several effects. If we had 4 engines running at 70% full power, let's call this 280, and we lose one engine, the other 3 can go to almost 100% power, and we can get back to 280. But these engines must stay in this position to keep the rocket flying straight. Adjusting a rocket engine's power up and down, called throttling, is not instantaneous. If the rocket experiences an asymmetrical force on the nose, it cannot adjust engine power quickly, and must gimbal the remaining engines to try to compensate. When the remaining engines gimbal, they come out of the stable configuration that is keeping the rocket on course. So far it's doing okay. Then the rocket starts to reach transonic speeds. Passing through the sound barrier is always a dangerous time. Parts of the ship are experiencing supersonic airflow, while parts are still subsonic. This causes rapid shifts in the forces felt by the rocket. As the engines try to compensate, they move out of their stable configuration. This causes the rocket to veer off course. The engines try to correct, swinging the rocket back, causing an overcorrection. And the rapidly changing forces overpower the remaining engines. Once it is clear the rocket is lost, the range safety officer activates the flight termination system, which has explosives positioned here, that are detonated to blow up the rocket. The number of engines your rocket has determines your ability to survive an engine failure. With one engine, the Copenhagen suborbital rocket cannot compensate for an engine problem. The Firefly Alpha has 4 engines. Loss of one will take out 25% of the rocket's thrust potential. The Astra Rocket 3.3 has 5 engines. Loss of one will take out 20% of its thrust potential. The Saturn V rocket used in the Apollo 13 launch had an engine failure. It was the center engine in this configuration, and they just burned the other 4 for a longer time period. A rocket with 9 engines will have more complicated plumbing and control software. But if it loses an engine, there is only an 11% drop in thrust potential, giving the rocket plenty of time to gimbal the other engines and increase their thrust. If the other 8 engines increase from 70% to 78.75% thrust, they will fully compensate for the loss of one engine. And with multiple engines, you can freely gimbal just one of them to make small corrections, keeping the others in a stable position to compensate for thrust loss. A Falcon 9 suffered an engine failure in flight and had no problem getting to a stable orbit and completing its mission. The Starship has its landing engines in the center. It can easily balance with 1, 2, or 3 engines running. The Starship booster will have up to 32 engines. The outer engines will be fixed in place, but can be throttled up or down for thrust vectoring. The inner engines will be able to pivot, allowing for control during the flip maneuver and landing. One engine failure would hardly have much effect. The other engines will only need to increase their thrust by 3.23%. Redundancy increases safety. The Starship system will fly hundreds of uncrewed missions testing and proving its components, before it ever carries people. Hydraulic systems have some delay, as the selector is physically moved or valves opened. Pressure is released and travels down the line, and actuators are extended or contracted. Let's take a moment to review how hydraulic systems work. Here we see the components of a hydraulic cylinder. There is a tube to contain everything, 2 inlet outlet ports here and here, a cap with seals to allow the actuator arm to extend without losing the fluid, and a piston back here. When we direct the fluid flow in one direction, we extend the actuator arm. We can position the control valve neutral to keep the arm extended, or we can cross that flow to retract the arm. Again, moving the control valve to neutral to keep it retracted if we want. Or open the valve to extend it again and hold it there. Now let's look at how an actuator system can be used to control a large high-pressure valve. Here we see a hydraulic actuator valve being assembled. And here is the actuator arm. Once all the seals are in place, we can place this actuator over a large butterfly valve. and put the valve in a pipe. We add our hydraulic lines, by controlling the flow of hydraulic fluid to the actuator, as you saw before, we can open this valve despite high pressure resistance. Once enough fluid has flowed through the pipe, we can reverse the hydraulic fluid flow going through these lines to close the valve. You will notice that this actuator has a stop screw adjustment and a mechanical locking mechanism to prevent it from opening accidentally. This is a beautiful example of a hydraulic actuator. Electric motors and actuators can potentially be much more responsive than hydraulic systems and have a lot of other advantages. There are a large number of electric actuators available to rocket companies. Some of them are very powerful and can last a long time. They require less maintenance than hydraulic actuators and are lighter and usually cheaper. Normally, battery power would be an issue, but with Tesla power packs available, SpaceX has that covered. Let's watch what SpaceX has been able to do with electric thrust vector control actuators. That seems amazingly responsive to me. Now we will need to see if the electric actuators are as robust as the hydraulic ones in operation. Let us know if you see any new information on these advanced electric thrust vector control systems, and stay safe. At Astra Pro Terra.
That's a quarter section of the Falcon 9 17-foot diameter fairing. It's 17-foot diameter, obviously, and 50 feet long. It's capable of taking the largest satellites in the world, and it could actually literally fit a city bus in that fairing. It's that big, because that's just a quarter section of it. It's made of carbon fiber. It's very lightweight, and uses the most advanced analytical techniques to optimize the mass. So it's actually, I believe, the lightest weight fairing of its kind as well. What we're looking at here is the Dragon spacecraft pressure vessel. So it's almost done. We just need to do the forward and aft bulkheads. It's actually upside down right now, but you can see the main hatch, some of the windows. The actual common berthing mechanism where it berths to the space station is, well, right there, because it would ordinarily be the other way around. And this is an actual flight fidelity article that's going to go through full qualification testing. Right. This area is dedicated to our Dragon spacecraft assembly. So you see various tools. That's for our heat shield, making the composite parts on our heat shield. Over there are the side shields and the nose cone. That's the engineering test article, basically engineering pathfinder for our heat shield for Dragon, which is to use a very advanced material called the phenolic impregnated carbon ablator, which is really the best heat shield material you could possibly have. And this is our engineering test article of our Dragon spacecraft. So it's not flight fidelity. The part we saw earlier we saw the welded piece, that's actually flight fidelity, but this was used as an engineering pathfinder to figure out how we might make Dragon, and actually it's been very useful. On the right there is a space station berthing mechanism ring. So that's an actual ring that will mate to the space station. There's another one on the Dragon itself, although the guide vanes aren't present. Here are various pieces like windows and pushers and frangible nuts, and these are structural bulkheads, structural reinforcing bulkheads. That's the little model we use to determine splashdown loading. So here we are in the east high bay. So we have two very large high bays. We're in the east one right now. The east high bay is used for Falcon 9 stage construction, and it's also temporarily used for storage, which is why you see various bits and pieces around behind me. This area under the high bay is used for Falcon 9 tank fabrication. So you can see behind me various barrel sections for Falcon 9. That's actually serial number 2. That completed tank is serial number 2 of Falcon 9. Serial number 1 is on the test stand in Texas. And then serial number 3 is in barrel sections on the floor. And we're getting ready to weld together those barrel sections and create our third tank, which would actually be the first flight tank. So the first one was a run tank, second one is a qualification tank, and the third one will see flight. That's a Falcon 1 second stage bulge former. So that's a classic bulge forming tool that's used to take two welded cones of a typical refractory metal like chromium hafnium alloy, and bulging it to a round contour, which is the optimized contour for maximizing the efficiency of rocket thrust. This cleaner here is also climate controlled, particularly controlled, and it's currently used for propulsion components, as well as temporarily it's used to do composite layout. So that giant tool you see there is the mandrel that's used to create the composite parts for Falcon 9. So it creates the interstage, the Dragon trunk section, and the propulsion section skirt. Anything that's a body diameter, a 12-foot diameter cylindrical part. And that'll be moved over to the actual composites area when we have that composites preparation room done, which will be fairly soon. This area is where we do a lot of the Falcon 1 structural assembly. So behind me, that's a Falcon 1 half section of a nose cone. That's the tool on which the nose cones are made. That's an avionics, or rather a payload adapter cone. That's another payload adapter cone. That's a mandrel for the Falcon 1 interstage, which is similar to the Falcon 9 interstage. In fact, the Falcon 9 interstage is just a scaled up version of the Falcon 1 interstage. This is a barrel section for Falcon 1 Flight 5. So we have Flight 3 on the island in the Kwajalein Atoll, ready for launch, almost ready for launch. Flight 4 is going to be right behind that. We'll launch in about 3 or 4 months' time. And then this is Flight 5, which will launch sometime in the first half of next year. We have a lot of customers that are interested in that, and we expect to do a deal on that fairly soon.